Okay, welcome back. I'd like to uh, start talking a little bit more deeply about the logic of hypothesis testing. In the previous video, we sort of did an informal argument about, what proportion of popcorn kernels would remain unpopped. Um, so we're going to revisit that for a few minutes, um, and then go ahead into a different scenario and kind of maybe formalize some things and understand what our arguments are. I'm going to be switching screens back and forth a little bit, so hopefully it doesn't um, get too confusing. But I will try to put a link to the website in the comment section of this video after I'm done for the one website I'm using. Um, so if you watched my video yesterday, we started talking about popcorn. So the goals of our video are going to be to understand the logic of hypothesis testing by comparing your answers to these questions. Um, so this is very important. This is the way I like to present this. What do I expect to happen and what actually happened? And the further apart your expectation is from what actually happened, the less confident you feel in your original expectation, which is like your guess. And then we're going to learn to establish a set of hypotheses and criteria to make a conclusion about a parameter. So we've used this word a lot, parameter, and we need to know what that means. That is a characteristic or a value associated with the population. And a lot of times, um, those are the things we're trying to estimate or make conclusions about. I mean, there's just too many complex problems, real problems where you're trying to. I mean, the perfect example is just elections and things like that. People go into elections and they try to determine what should they who how what proportion of people or percentage of people voters should they reasonably expect to vote in their favor. So um, that's a number that is you know hard to you can't really calculate it without getting responses from every single voter possible. But you can estimate it doing a random sample, and that's so important to understand. Is that we can learn a lot about a population just by taking a random sample, and the random part we've talked about is very important because with a random sample, you are likely to get a sample that represents the population and its characteristics really well. So let's go to the popcorn thing. So yesterday, the video was you had a bag of popcorn, and I hope that some of you actually tried it and went along with me on it. But the question was like, what proportion of popcorn kernels tend to remain unpopped? And we were talking about the population of all popcorn kernels, and I used a specific bag or specific type of popcorn, but um, for the purpose of what we're talking about, I mean, there's a ton of kernels produced by that one company. So, apologize for the ding. Uh, so what we did was we thought about like, well, what do you think that would be? And to me, I mean, I had no idea. I just took a guess. I said maybe 15%. So 15 out of 100 kernels, I would think would remain unpopped. And then we kind of carried that out. I mean, we actually had a sample, and I want you to think about this popcorn bag yesterday. I mean, in some regard, you could think of it as a random sample of all kernels from that company. I mean, when the kernels come off the line and they get filled in bags, I mean, there's no reason to believe that. I mean, they're not. There's any. It's a random process. I mean, they're just randomly sorted into the bag. So, I mean, however many kernels were in there, and I think we had about 262 of them or something like that. I mean, it's our sample size, random sample of 262 kernels from this population. Um, and we wanted to see, like, are we a good guesser? I mean, this is basically what it comes down to. Are you a good guesser or are you not a good guesser? So my guess is 15%. And let's think about, was I a good guesser or not? So here's kind of what we went through yesterday. So we talked about a few things here, like the parameter of interest and the population of interest. I'm going to try to use different colors here to type. I will also link this document in the video when I'm done. If I forget and you are one of my students, please email me. So the parameter of interest. What is that? That is what you are trying to estimate or learn about. in the setting is the true proportion of unpopped kernels in, now I'm going to kind of blend these two together, in the population of all kernels from whatever manufacturer you had, from this given company. Okay, that's what we're trying to estimate. I'm just going to ignore some typos and things like that, or hyphens, and so I'm not going to go back and fix all that stuff. Parameter of interest in the settings, the true proportion of unpopped kernels in the population of all kernels from this given company. We typically denote that with P, lowercase p, the true proportion, the population proportion. So we have the parameter of interest, which also identifies the population of interest in its description. Okay, so like, what were our hypotheses yesterday? So yesterday, a hypothesis, we kind of talked about just like a guess, and so my initial guess was that the true proportion was of unpopped kernels would be 15% or 0.15. So that is our initial guess. So the initial hypothesis was that P is equal to 0.15. So this is one hypothesis. Now, what we also talked about is if for some reason your initial guess or hypothesis was wrong, what would you use as a suitable alternative explanation to what you think is actually happening? So yesterday I kind of argued, you could argue maybe you think it would be less than what it is, maybe you think it's just not equal to it, which means it could be higher or lower, or maybe you think it's going to be a little higher. So to me, I thought, if anything, truly, if I guessed 15%, I thought that would actually be a little too low if I was wrong. So my alternative hypothesis and the alternative hypothesis or explanation, if I'm wrong, is that the true proportion is maybe bigger than 0.15. Okay, so here some of you may have felt differently. Some of you may have thought there were going to be 40%, or guessed that P was 0.4. So maybe your alternative is it's less than 0.4. Doesn't matter. That's just, what's your alternative explanation going to be if you think, if you end up being wrong. So we have two hypotheses. We're going to come back here in a little bit and formalize some of this. But these are your two logical hypotheses. Your initial hypothesis is your initial guess. And the alternative hypothesis, I should use the same tense, is what's your alternative explanation is that it could be bigger. So this is where it gets, this all is really important, but this is where I think I wish I could have a conversation with all of you face to face about this. Is what rejection criteria did I use to reject my initial hypothesis, my guessed expectation, in favor of my alternative? So like, what criteria did I establish? So I wanted us to think about that, and I hope you remember yesterday I said, like, what's your gut feeling? So you take your guess. Mine was 15%. It's like, okay, so when I really go and pop this bag of popcorn, what proportion would what would make me think that my 15% guess is actually wrong? And I sort of said that we can think of that as maybe, okay, if it was less than 10%, the sample proportion, then maybe I would rule out 15. If it was over 20%, then maybe I would rule out 15. But I sort of established those. So yesterday, my rejection criteria was pretty much that if the sample proportion, which we usually call p hat, right? We call that p, with a little hat on it. So where's that thing at? There it is. P hat. If the sample proportion p hat was larger than 0.2, I decided that I would reject my initial guess of P equals 0.15. In other words, 0.2 is too far away from my expectation for me to believe that I guessed correctly or that my guess is reasonable. Okay, so I just kind of established that, and so this is something that's important. That was established by me, and I want us to think about, like, when we do the next problem here. The question is, what happened, what do you expect to happen, and what actually happened. How far is too far? If I would have got if I would get a sample proportion that was 16%, well, like, is it reasonable for me to rule out 15%? I don't know. But we have to establish some sort of rule that says, you know what, this value we got is just too far away for our initial guess to be right. Okay. So this was my criteria. If it was if the sample proportion p hat was larger than 0.2, then I would reject that my initial guess was correct, and I would start to favor that maybe my alternative explanation that the true proportion of unpopped kernels is larger than 0.15. So, what did my sample data tell me? And yesterday, I have the data here. So we took a random sample. I believe for me it was 262 kernels. So that is, throw that in there for a little notation. N equals 262. And we found, so when I did this yesterday, 77 unpopped kernels out of 262 total kernels. In other words, P hat, our sample proportion of unpopped kernels, I believe, was about 0.29. So it was about 29%. So what does this mean? This means in our sample, we observed about 29% of the kernels remained unpopped. So great, I got sample data. I have some information. What conclusion did I make and why? Well, here's what happened. I took this sample and I got 29% were unpopped. And what I did was I looked at my rejection criteria. I mean, it's as easy as comparing. It says, well, 0.2 is too far away. So 0.29 is clearly bigger than 0.2. So since 0.29 is greater than 0.20, I reject my initial hypothesis that P is equal to 0.15 in favor of P is greater than 0.15. The sample data, which this is our evidence for our conclusion, data-based conclusion, the sample data suggests that the true proportion of unpopped kernels in this population is larger than 0.15. Okay, so that was my conclusion. That was it. I compared it to what I expect to happen and what my criteria was. And I said, you know what? It's a little too high for me to believe that 0.15 or 15% is probably a reasonable guess. So, I mean, that's really what this comes down to. So, the last question, which I think is important here to understand, is like, some of you should be saying, like, well, like, yeah, that makes sense, but also depends on your guess, doesn't it? Like, on your initial guess. How did it depend on my? I'll add that in there. Initial guess. Well, it depends a lot on my initial guess. If I would have guessed at the beginning that there would have been 29% unpopped kernels, I would have felt pretty good because I would have hit it spot on. I would have said, oh, wow, I was good. I guessed exactly correct. I guessed perfectly. if I would have guessed 10% at the beginning, I would have felt even worse than I do now because 29% is so far away from 10%. So, um, so how does it depend on this? How does your conclusion depend on? It depends a lot. The closer your expectation is to what actually happened, it changes your conclusion. It changes your rejection criteria. It changes, um, you know, what you are going to what you're going to rule out. So it depends. It completely depends on your initial guess. The closer your initial guess is, remember that's your expectation. What do you expect to happen? To the actual sample proportion, the better you will feel about your guess being plausible. In other words, like it's reasonable. Plausible, I'll use the word reasonable. I think it's better. Reasonable. Okay. So, and the further away your sample data is from your guess, um, the worse you're going to feel. And then finally, your guess, your initial guess, completely establishes your rejection rule. Like, I mean, you have an expectation. You're the one who's going to say, like, what's too far away from my expectation to rule it out. So, for me, if I would have guessed that it was, if I would have guessed 20% at the beginning, and I gave myself, said, well, okay, if it's over 25%, then I would probably rule out my 20. I mean, I still would have made the same conclusion here. 29% still too far away from 20%. But if I would have guessed 25% initially, just started with a 25% guess, and I established that okay, maybe more than 30% would be my rejection rule. Well, then I wouldn't have rejected this because 29% it's not that far away from 25. So I'm just going to put a little explanation in here about what I mean by that. So, for example, if my initial hypothesis, your initial guess, was that P is equal to 0.25, I probably wouldn't feel as good about rejecting my initial guess because 0.29 is not that far away from 0.25. Okay. If my initial guess was P equals to 0.27, I would feel pretty good about that number being reasonable since the sample proportion 0.29 was pretty close to it. So it does depend. It's really what you're really, and I think two things to remember. What do I expect to happen and what actually happened? And the final thing is you are really trying to figure out, you're really testing how good of a guesser you are. That's one way to look at it, okay? So let's look at another problem here. So this is the logic behind the hypothesis test. So let's look at M&Ms. Here's another situation. So M&M's claims this color distribution for the population of all M&Ms produced. Tony doesn't think that these claims are correct. In particular, he thinks the actual proportion of blue M&Ms is less than advertised. To test the validity of this claim made by the company, Tony opens up a bag of M&Ms and finds that 7 of the 37 are blue. Okay, so let's go through here for a second. Here's the claimed color distribution. So, just so we understand what this is saying, M&M's claims that 14% of all M&Ms produced are yellow and 24% of all M&Ms produced are blue. And we're talking the classic M&Ms. Not like with the peanuts or anything like that, and it's just the standard M&Ms. So, what is the parameter of interest? Well, what are we trying to learn about? I mean, we're trying to learn about it says right here, bad grammar. Right here, the actual proportion of blue M&Ms. That is the parameter of interest. So the parameter of interest is P equals the true proportion of blue M&Ms produced in the population of all M&Ms. Okay, so we identified the parameter of interest right here, the true proportion of blue, and the population of interest within that. That is a requirement for full understanding of the scenario. We got to be able to define both. So, what hypotheses is Tony testing? So, what is he testing? He is testing that the claimed proportion is 24%. He's trying to test that out, and he actually feels that maybe it could be less. So, the initial hypothesis is that P is equal to 0.24. I mean, that's what's claimed. So that's what they're claiming. That's like Tony's guess. He's like, best guess is 24%. I mean, until I prove them wrong, I gotta believe it, right? So the initial hypothesis is P equals 2.24, and the alternative hypothesis is P is less than 0.24. In other words, Tony's trying to say, like, he says right here, he thinks that it could be less than advertised, less than that. So those are the two hypotheses. So why is this important? Well, what should he expect when he opens the bag? Well, according to the company, when Tony opens the bag, he should expect 24% of the M&Ms to be blue. So that's the expectation. I mean, there's no other reason to believe they're wrong. I mean, until you open it up, you have no clue. So you should expect 24% to be there. So now here's the fun part. Here's the interesting part. Okay. So we're going to talk about this rejection criteria a little bit more formally for a few minutes. Because I'm sure, and I know at least one person that I know I've had conversations like with them about, it's a little funky that you get to pick your own criteria. I mean, I would hope people don't feel maybe not that comfortable about it, but if we're just picking them like whimsically and whatever we want them to be, that's fine. It's a very informal thing to do. However, there's better ways of doing that, and one way to do that is to argue in probability. Okay, so I want us to think about what we would do, how we would create a rule to reject this hypothesis. In other words, saying that, what, the sample data we have is nowhere near what they're claiming, and how to give maybe an argument for that using some probability. And so one way to do that is to say, is to establish a probability cutoff and say, like, well, if I get the sample data and it's got a really low probability of occurring, under our guess, like under our expectation right now is 24% blue, if it's got a really low probability, then that means it's probably pretty far away from the 24%, which means our 24% is probably wrong. So we established this using a couple accepted statistical, a couple accepted, probabilistic cutoffs. So we call this, what we do is we establish the rejection criteria using probability. We set it's called significance level. A lot of times we denote this significance level, this probability we're going to set, with the Greek letter alpha. Looks like a sideways fish. Greek letter alpha, which will tell us when to reject our hypothesis, our initial hypothesis, I should say, our initial hypothesis, and when to not reject it. Okay. So alpha is a probability. This is a certain probability, a certain level. It's a percentage. So what we're going to do is we are going to, our rule, our rejection rule is going to be, we are going to use a 5% significance level for our test. This means that if our sample data occurs with our sample data or more extreme, something even, I mean, like in the popcorn example, we got 29% was our sample data. But if I would have got 35%, that's even more extreme than 29. So our sample data or more extreme occurs less than 5% of the time that under our initial guess. That's our assumption under our expectation. Then we will reject the 24% claim. So in order for us to reject the 24%, which is our expectation, we have to get a value, our sample proportion has to be far enough away from 24% to give us a really, really low probability. And we've seen distributions, right, with like, think of the normal distribution or the binomial distribution, where the tails are very, very thin, and there's not a lot of probability there. So this is one way, this is the formal way we set what's called a significance level, and we use that to evaluate our test. So what we're going to do is we are going to give ourselves, an expected distribution. So we're going to go ahead and simulate some things for opening up these bags of M&Ms. So to do this, we are going to build our distribution of what we expect to happen. So using simulation, we are going to build a distribution of sample proportions that we should expect to occur under the company's claim that 24% of the M&Ms are blue. So when we do this, I mean, we should really see a lot of bags have about 24% blue. So we're going to use this website here. This is called Stapplet, STAPPLET.com. Variable name. We're going to call it color. And we're going to give it a count. So we had blue and not blue. So if we go back to our problem for a second, we're going to go ahead and use what we have from our sample to kind of set this up. We had 7 of the 37, so we had 7 that were blue and 30 that were not blue. So in our sample, just to kind of get this set up here, we had 7 blue and we had 30 not blue. Begin analysis. This is just representing our sample data that we took. Shows us what our relative frequency is, which is our sample proportion, which we'll get to in a minute and talk about. But what we want to do is we actually want to build a distribution of what we expect to occur. So here's what we have. We're going to simulate this, giving a sample percent or proportion. The category we're interested in is like, do we get blue? So our success is going to be we pull out a blue M&M, and we're going to simulate the distribution of sample percent for samples of the original size. So if you look at this, we took a total of 37. We learned that sample size is important. I mean, the larger the sample you take, the more information you gain about the population. So we're going to make sure we use a sample of size 37 that the true percent is equal to. So the hypothesized percentage is 24. This is what M&M's claims. They claim a 24% blue rate. So let's see what happens. So like if they are telling the truth, if M&M's is really telling the truth that they do actually produce 24% blue, let's just take a sample of that population and see what happens. So let's take one sample, hit add sample. So this thing right here, it told us we took one sample, and this sample from a population of 24% blue gave us 27%, which makes some sense. I mean, if there's supposed to be 24% blue, then it shouldn't be that unlikely that you get 27% blue. So let's add another sample. So we open another bag. So this little dot right here represents one bag of 37 M&Ms and its proportion of blue M&Ms. Add a sample. Now we have two. Okay, this time, this sample we took had 32%. Okay, so that's a little further from 24. Let's add another one. Okay, this was 18 or 18.9%. So again, a little lower. So every time you take a sample, one thing we also learned is that they're not always the same. So we take a sample, take another sample, take another sample, and we start to build. Right now, we've opened 5 bags of 37 M&Ms, and we start to build this distribution. You can see the average of all of those percentages is what we expect to happen. So if I add, let's say, 100 more to this, so we'll have a total of 105 open bags. Take a look at what happens here. If you look at this distribution, this should make some sense. The expectation when Tony opens this bag is there's going to be 24% of those M&Ms are going to be blue. So when you look at this, this should make some sense. Like most of these bags would be contain around 24% blue M&Ms. Sometimes you get some things that are a little too high, sometimes a little too low. But this is what would happen if you just started ripping M&M bags off that line, that production line, and opening them up. And I mean, they're telling you that you should get about 24%. I'm going to add another 100 on here. So let's do another. So we'll have 205 open bags of M&Ms. Okay, and we see that, okay, more clustering around 24%. Here's another. So we've opened now 305 bags of M&Ms, and we see like they are pretty clustered around the 24%, as they should be, because that is what the company is advertising. Okay, so what we're going to look at is, how can we use this data right here to answer our question? Okay, so our question is going to be is about like what are we doing? Like, how do we actually feel about this 24% claim? Because Tony is clearly skeptical that this 24% claim might be too high. I mean, he says it right here. He's worried that it actually might be less than 24%. So this distribution we just built here. I'm gonna go ahead and just take a screenshot of this, and we'll summarize for a second. So this distribution we built, it says, how is this distribution consistent with the company's claim? Well, it's very consistent. I mean, the most important part about this is that it's clustered around 24%. The sample proportions, and there are 305 P hats on here. That's what these are. You took 305 samples. from this population, there are 305 of them. You've opened 305 bags. The sample proportions tend to cluster around 24%, as they should, since 24% is what we expect to happen. That's our expectation. Sometimes a little higher, sometimes a little lower, but generally we should be pretty close to 24%. Okay, so it does reflect that because that is what we expect to happen in our initial hypothesis or our initial guess, or in this case, the claim made by M&Ms. So the most important question then is what actually happened when Tony opened the one bag that he had. So what actually happened was Tony's real bag of M&Ms, because remember, the simulation, we've learned about simulations. Simulations, it's like fake it till you make it. And you fake the trials to build a distribution of what you expect to occur. And then you can use that information to help you answer your questions. So Tony's real bag of M&Ms had 7 of 37 M&Ms that were blue. So what does that mean? That means P hat, this thing, was equal to 7 out of 37, which is roughly, little number crunch here, 19%, so 0.19. That is the sample proportion. So Tony's real bag had this. So Tony had 19% of blue M&Ms in his sample. Okay. So the question is like, what actually happened, and then where does it fall within this distribution? So if you look at this, 19% falls somewhere like right around here. Okay, so 19% falls somewhere right in here, and actually a little closer to here, right about here, and so we need to kind of look at. Sorry, Mom. We have to look at where this whole thing. I'm sorry, I got to back up. I didn't anticipate that phone call. The 19% falls right here. Falls right here on. This is the 19% column. So this is what we what we got. We got one of these. Ours, Tony's sample was one of those dots right there. Okay. So it falls right here. So here's the big question. This is what you got to look at. So what do you expect to happen and what actually happened? Okay, so compare what Tony expected to happen, his initial guess, to what actually happened, which is your sample data. What conclusion should Tony make and why? So let's take a look for a second. So Tony expected to get 24% blue in his sample, but Tony got 19% blue. So what conclusion should he make? Well, that is based on our rejection criteria. So Tony needs to look at the rejection criteria, which said if our sample data or more extreme occurs less than 5% of the time, we will reject the 24% claim. In other words, it's probably not true. So we just need to figure out this probability. So what's the probability that we have our sample data, which in this case is 19%, or more extreme than that? So more extreme would be something even smaller, this direction. So if I go back to this this screen here, I'm looking at 19%, less than or equal to 19. Here's 19. Um, here's the region, the more extreme. Like, I mean, there's sometimes you get 10%. If you look at that and you count them, it says there are 106 dots, about 34.8% of them in the selected region. In other words, we expect 19% or worse to occur about 30, almost 35% of the time. That is not a small probability. So if you look at this, if you notice, 24 is somewhere in here. 19 is really not that far away from 24 with respect to the whole distribution. So this probability, since it's bigger than our 5% rule, we cannot reject the 24% claim. Like, this 19% is pretty common. If they're actually producing in 24% claim like they say they are. So this little probability here is not small enough for us to reject. Now, if we would have got, let's say our actual sample data was 10, well, look at this. I mean, this is a 10 or less is only 1.3% of the time. 10 is really far away from what we expected. So it would make sense for us to reject the 24% claim because 10 shouldn't happen that often, or worse. And if you look at this probability, 1.3%, that is definitely less than the 5% rule we established. So that does not occur very frequently at all. But the one that we actually got, which was 19, has a pretty high probability of occurring. So what we would say here is what actually happened was we see that about 34.8% of the time we would get 19% or less if the 24% claim was true. Since 34.8% is bigger than our 5% criteria, or significance level, in this case, that's the technical term for it, we cannot reject the 24% claim. It is possible that M&Ms are produced with a 24% blue or 24% blue percentage as the company is claiming. Can't rule it out. Okay, so it wasn't too far away. 19% wasn't far enough. So we're gonna go back through here and do a little just vocab for a minute or two, and we'll go from there. But we're gonna continue working with this hypothesis test, and establish a little bit more formally every time we do it. But this is the logic. Like, what do you expect to occur? What actually happened? And is it too far away based on your criteria? So I'm going to go back through here for a second, give you a little vocab. So a little vocab, which is more formal. Okay, hypotheses. I use the words initial hypothesis because we've been talking about guessing and things, and I wanted you to think in terms of guessing and stuff like that. So an initial hypothesis is really called, I'm going to put this in purple. A little vocab will be in purple here. So an initial hypothesis, statistics, we usually call this the null hypothesis. Null meaning at the beginning. So a lot of times it's always denoted, I shouldn't say a lot, always denoted as H with the subscript 0. Okay, that stands for null hypothesis. And then we have what's called the alternative hypothesis, which I did use that word, or that phrase, I mean. And we typically denote that with, similarly, H sub A for alternative. That is the notation for it, because you should always have an alternative explanation if you're going to reject the initial guess you have or the initial claim that is being made. So in our problem here, what we would write as statisticians, we would write h sub 0, put a little colon, p. So we said we predicted to be, we guessed it to be 0.24, and then we would write this underneath it is that p, what's our alternative was that it was less than 0.24. Okay. This would be the formal definition of our hypotheses. So initial null hypothesis is your guess, your expectation. What is your guess or expectation? I want you to think about that. That's what that is. That's what that means. Okay. What is your alternative explanation if your initial guess is wrong? That is what that is. Okay. Rejection criteria. Gave you this word right here, set a significance level. It's always denoted with alpha. Significance level alpha, that is preset and predetermined. Common significance levels are 5%. Are 5%, 10%, and 1%. Could really be any probability you choose, but you set that, or it is set for you to use as your rejection criteria. So, and these establish the rejection criteria for your test. Okay. If you have a probability that is smaller than those, you reject your null hypothesis, the initial guess you had. If you have a probability that's greater than that, then you cannot reject it. And we'll clear that up here in a second before we're done. 5%, 10%, 1% should, I don't know if they'll sound familiar, but when I say it like this, they will sound familiar. You have a 95% confidence interval corresponding to a 5% significance level. A 90% confidence interval corresponds to a 10% significance level, and a 1% significance level corresponds to a 99% confidence level. But those are just some of the underlying connections we have in our in what we're learning. Okay. So we have okay. What actually happened? Here we go. So the last little vocab for this is down here. So in this comparison, compare it to what Tony expected to happen to what actually happened. So this probability that we got right here in purple, that came from from looking at our distribution. This probability, 34.8%, is called the p-value, which stands for probability value. No one really ever calls it that, but of the test. And what is this thing? The p-value is the probability of your sample data occurring under the assumption that you initially guessed correctly. In other words, the null hypothesis is true. Okay. So in this case here, our null hypothesis was that we expect 24% blue. We found that we got 19% blue, and looking at our distribution, we saw that 19%, so our proportion 0.19, or worse, more extreme, occurs almost 35% of the time, which is a pretty high probability. So it was not less than or lower than our 5% significance level. So we did not reject our hypothesis. So the p-value p-value is compared to the significance level in order to make a conclusion. If the p-value is less than, throw alpha in here because that's what the symbol for significance level is. Its p-value is less than alpha. That means our sample data was far from what was expected, low probability of occurring. So we should reject our null hypothesis in favor of the alternative. If the p-value is greater than the significance level, then our sample data was close to what was expected. So we do not reject the null hypothesis. Okay. So those are a couple of vocab words: a p-value, a significance level, and a null and alternative hypotheses. So we're going to use these hypotheses we should be able to establish from the context of a given situation. Significance level is set by you as your rejection criteria, and then we compute a probability to compare it to your significance level and reject accordingly. Okay. Last comment, and let you go. Thanks for hanging there with me. Looking at this, what is the parameter? Our initial hypothesis and stuff up here from the popcorn problem. We would write that these would be our hypotheses for this. Copy these up there for a second, just so we practice seeing some of these. Write a set of hypotheses for this. Okay, so this would be p equals 0.15, and for this one, I believe I said it was greater than. I thought it would be bigger than 0.15, so this would be an appropriate set of hypotheses to describe this situation. We did not formally establish like a significance level for this. It was kind of just an informal argument, but if we did that, we could compare it to a p-value. We didn't actually calculate that for this first. I just wanted the logic to set in about what we're actually doing. So very important. This is really the one of the big parts of statistics is testing out a claim, because you want to know if those things could possibly be true or not. So remember, what do you expect to happen and what actually happened? The further away the actual sample data is from your expectation, the worse you should feel about your expectation. So you would reject it. Okay? We're going to be doing some things as we go, so if you have any questions, let me know. Thanks for hanging out here.